All right. Well, welcome back, and I hope you enjoyed the niceties of winter sports in North Carolina and watch everything slows down and actually stops for 2 days or 3 days or whatever the case may be. Good 2 days here on UNC Charlotte campus. So, as always, when something like that happens, we have virtual classroom day, which means you can't fall behind in the Calculus 1. So I noticed that I sent everybody an email with the direct links to make sure you guys don't fall behind, and hopefully you'll watch the rest of 1.5 that I didn't get done basically last Tuesday, and basically we covered all of 1.6. And I'm sorry it had to be in two different videos here. It should have been one big video, but when I teach this class from one semester to the next, I never know where I'm going to end up, and it never figures out I'm going to end up at the exact same spot as I do the following semester. So I had to kind of edit one video and then put the other video on top of it. So that's pretty much how I came up with this mess. So, but I thought, and also just to let you guys know, just good practice here, modules, where all our good stuff's located at. You know, I also put out here, you know, you've got your course calendar right here, so you want to keep up with exactly what I'm doing every particular day of the week and stuff and what we're supposed to be covering. Here are your notes. Here's some more information and stuff. But I did put a new insert into this thing to make easy access. Now we got the little Panopto link over here on the corner over here, Panopto recordings, but I made a master link right here to the Panopto videos for our class. So if you click on it, what you get to see are the videos actually in order from high to low here, and you can actually pitch which section that you're in if you want to watch your class, if you want to watch the other classes. Here were the snow day videos, so the next video I'm going to insert will be the one for our class, which will go down below it, and I'll keep doing this throughout the rest of the semester and stuff. So, also, you should have done, if you've been paying attention to your syllabus and the like, we are, you have your pre-section quiz on section 2.1, which is due when? Today. Actually, I put it tonight at about 11:30. So if you haven't done it yet, don't fall behind, because I can't reopen these things and stuff, and the like. So make sure you do the pre-section videos before you come to class. Take the quiz. Make sure you master everything, and then come to class, take some notes, and then you got your web work and stuff. And you'll notice right after 2.2, we're about to have our first test. But do check your syllabus for the dates and the like on the syllabus and stuff. So just in case you wanted to know, you haven't posted the test yet, when it's going to be. Yeah, I actually did. Yeah, there we go. Click on this thing here. And click on, well, actually, here comes the master one right here. What does it say our first test is going to be? Yeah, that's right. February the 6th, which is a Tuesday. Your homework that I'm going to be posting will be due on February the 1st. There it is, and we're right here at 2.3, so I'll start announcing homework sets and stuff like that for you guys to turn in and stuff. So there you go. So, okay. And I always try to make sure that a test, so I may go dabble in section 2.3 and section 2.4, but the test will only cover through section 2.2. I'm trying to buy you some extra study time to make sure you master this stuff. This first test is going to be on limits. So let's go ahead and get started. But because we had a wonderful snow day here, and your ability to watch awesome videos that your professor posts for you guys and stuff, I want to make sure you understand this material. So I want to sit here and work these particular problems for you guys. All right. I try to do one of each different kind. This is from section 2.5, but pretty much 2.6. This is section 1.6. Section 1.6 on the idea of limits here. I want you to take the limit as x approaches 3 of 2x squared plus x plus 1 divided by x squared minus 6x plus 9. What's the first rule of limits? Plug it in. So when I plug this thing in, I'm going to get 2 times 3 squared plus 3 plus 1 divided by 3 squared minus 6 times 3 plus 9. 3 squared is 9, times 2 is 18. 18 plus 3 is 21, plus 1 is 22. Divided by 3 squared is 9. 6 times 3 is 18. 9 minus 18 is negative 9, plus 9 is 0. It's a number divided by 0. Now, in section 1.3, we would just declare this thing does not exist and move on to the next problem. But you've already covered section 1.6 now. So we've redefined this. So when you got a number divided by 0, the answer is either going to be infinity, negative infinity, or does not exist. And the only way for you to figure that out is this is the example where you actually break out the t-bar and actually start plotting some points. And you don't have to plot many points. You just got to plot enough points to see what's going to go on. And this is when you break out doing the one-sided limits. So I'm going to take the limit as x approaches 3 from below of 2x squared plus x plus 1 over x squared minus 6x plus 9. And I'm going to draw a little t-bar there. And I'm going to take the limit as x approaches 3 from the plus side of 2x squared plus x plus 1 divided by x squared minus 6x plus 9, and do my little t-bar there. Now, you know when you do the one-sided limits, when you get this number divided by 0, you're going to get an answer. It's either going to blow up to positive infinity or it's going to blow down to negative infinity. Just got to figure out which one it's going to be. So, let's plug in a number close to 3, but slightly below 3. I'm going to go 2.9 and 2.99. All you need is a couple of points. You want to show you that it's getting close and even closer. It's going to either blow up or blow down. It's going to get big negatively or positively. Let's see here. So this is when you use the handy dandy calculator on this thing. And here we go. And I'll blow this up in the back so you guys can see this a little better here. All right, I'm plugging in 2.9. So it'll be 2 times 2.9 squared plus 2.9 plus 1, and you need to put parentheses around your entire numerator there. Got those guys. And then I'm going to divide that by parentheses, another parentheses, 2.9 squared minus 6 times 2.9 plus 9, and close parentheses for the denominator. And I get 2,072. Which tells me it's pretty much going to positive infinity, but I got to show you that. So now I'm going to plug in 2.99 in for all my little x's. So I'm going to go in here and insert a 9, so the 2.9 turns into a 2.99 squared minus 6 times 2.99 plus 9, and I get, there it is, 218,702. Clearly, as this approaches 3 from below, what number are we approaching? Positive infinity. So the answer for this one is positive infinity. Now I'm going to do the exact same thing, but I got to do the right-sided limit. And I need to go take the limit as x approaches 3 from the plus side or from the right side, which means I'm plugging numbers like 3.1 and 3.01 into my function. So I'm going to use the same thing as what I just did before. I'm going to second entry, recalls it back down, and I'm going to go and change all those 2.99s to 3.1s. 3.10, I guess. 3.10, this is 3.1. 3.10 squared minus 6 times 3.10, and I end up getting 2,332, and then change those 3.1s to 3.01s. And I get 221,302. So as I go from 3 from the plus side, this side is what? Going towards infinity. So I get infinity. Therefore, very important, what exactly is the answer for the limit as x approaches 3 of 2x squared plus x plus 1 over x squared minus 6x plus 9. What is my answer? Infinity. And the reason for this is when I take my limit from below, it's blowing up. It's going towards infinity. When I take my limit as x approaches 3 from above, I'm still going to infinity. As long as I go to the same thing, what that thing is my answer. So remember, with a number divided by 0, there's 3 cases. You're going to have left side and right side going to infinity. That would mean the answer is infinity. You could have the left and the right side both going towards negative infinity, which would mean the answer is negative infinity. And if you got the answer that one side blows up to positive infinity, the other side blows down to negative infinity, the answer is does not exist because they're not going to the same thing. So you can still get the does not exist answer. It could be like this or like that. Does that make sense? There are 3 cases for the number divided by 0. This one was infinity. The other part of section 1.6 you need to know is this. Taking the limits as x approaches either positive infinity or negative infinity. Here's one. Take the limit as x approaches positive infinity of 2x squared plus x plus 1 divided by x squared minus 6x plus 9. Yeah, I just copied the same function now, but it's a different limit. We're taking the limit as x approaches infinity. This is called the horizontal asymptote of this thing. Now, because when you take the limit as x approaches positive infinity or the limit as x approaches negative infinity, you're finding the horizontal asymptote. You can use that stuff from high school, algebra 1, algebra 2 stuff about the horizontal asymptote theorem. You know, the degree of the top versus degree of the bottom. I went over that on that video you guys are supposed to be studying and stuff. So, when the degree of the top is less than degree of the bottom, the horizontal asymptote, or the limit as x approaches either plus or minus infinity, is going to be 0. Degree of the top is less than degree of the bottom, you get 0. When the degree of the top is equal to the degree of the bottom, you get the ratio of the leading coefficient of the top over the bottom. And when you take the limit as x approaches infinity or negative infinity of, and degree of the top is bigger than degree of the bottom, you get something called a slant or oblique asymptote. You don't get a horizontal asymptote. Okay? So when that happens, you're either going to get infinity or negative infinity as an answer. So these are the cases for this. But here's my point. I can look at these problems as well as you should and figure out what the answer is. What is the limit as x approaches infinity of 2x squared plus x plus 1 divided by x squared plus minus 6x plus 9? The answer is 2. The reason why being the degree of the numerator is 2. The degree of the denominator is 2. Therefore, the limit is going to be the ratio of the leading coefficients. Leading coefficients is officially 2 over 1 or 2. Great. You got the answer. However, this is calculus. I told you guys at the beginning of the semester that calculus is not more about than just getting the answer. I can show you tricks on looking at stuff like this and you can get the answer. But if you put down the answer is 2 and circle it and declare victory, well, I'm sorry, it's a 10-point problem. You didn't show any work. I have to take off at least 15, 20 points off this thing. Because no work means no credit. And I'll even take off extra points showing me crap. I want to see the work on this stuff. And this is the work I expect to see. We had this property that when I take the limit as x approaches either plus or minus infinity of 1 over x to any power, it's always going to go to 0. So we're going to use this property. Now, what is the degree of the denominator? The degree of the denominator is 2. So the trick is I'm going to multiply both the numerator and denominator by 1 over x to the degree of that denominator. So I'm going to multiply the top and bottom by 1 over x squared. Officially, it's a ratio of 1. It's not going to change the problem. And I put parentheses around this stuff, and I'm going to distribute through the numerator and denominator. This is going to give me the limit as x approaches infinity of 2x squared times 1 over x squared is 2, plus x times 1 over x squared is going to be 1 over x. Go ahead and reduce it down in your head. 1 plus 1 times 1 over x squared is going to be 1 over x squared, divided by x squared times 1 over x squared. The x squares cancel. You're left with 1. Minus 6x times 1 over x squared. Well, one of the x's cancels. That just leaves you 6 over x. And plus 9 times 1 over x squared is 9 over x squared. Now, using the property when you're taking the limit as x approaches either plus or minus infinity of 1 over x to a power, as the denominator gets bigger, the overall fraction goes to 0. 1 over a million is a millionth, is going towards 0. And you're left with, in your numerator, 2 plus 0 plus 0 divided by 1 minus 0 plus 0. It's 2 over 1, which means the answer is 2. That's the work we want to see. That's when you get the full credit. Yeah, you're right. Answer's still 2. It doesn't change that. And it's awfully nice to be able to look at a problem and know what the answer is even before you start. But you've got to show your work. The ones that tend to frustrate students, and this is why I put this one up here, because I had lots of folks come by and ask me about something like this because it bothered them. One of these problems that you don't exactly have polynomial divided by polynomial. We got limit as x approaches negative infinity of 5x minus 2 divided by the square root of 16x squared plus 5. Okay? Now, once you get good at these things, you can look at the problem and tell what the answer is. Okay? But there's a trick to it. Now, the trick is this. First off, you've got to figure out what the degree of the denominator is, just like we did before. Well, degree is x squared, but something weird because you're taking the square root of it because it's not really a polynomial here. But what is the square root of x squared also known as? X. So it's x to the first power. So I'm going to multiply both the numerator and denominator by 1 over x to the first power. However, I've got to rewrite the denominator 1 over x squared because the function that I'm going to try to distribute through is a square root. So you can rewrite 1 over x as 1 over the square root of x squared. But you've got a problem. When you introduce a square root into a problem, you got two options in this world. You got plus square root and you got minus square root. Which square root would you take and why? Plus or minus? You're going to take the negative one. And I'm going to explain why. You're going towards negative infinity. This ratio has to be the same. 1 over negative infinity divided by 1 over negative infinity. But when you rewrite 1 over x as 1 over the square root of x squared, when you plug in negative infinity, you got negative infinity squared, which will become positive infinity. And when you take the square root of that, that's going to be positive infinity. And this will be 1 over positive infinity, but this is 1 over negative infinity, and that's not the same ratio. Because of the negative infinity we're taking the limit to, this has got to be the negative square root. So it's 1 over negative infinity, and put the negative in front of the square root, now it's 1 over negative infinity. It's the same thing. So now you're going to distribute. So this is equal to, and again, you keep writing the word limit until you actually plug your number or infinity in here. The limit as x approaches negative infinity of 5. X times 1 over x, the x's cancel, you get 5, minus 2 times 1 over x is 2 over x, divided by, now you want to combine these two radicals. So you're basically got a square root of 16x squared plus 5 divided by a negative square root of x squared. Well, remember you can combine radicals. A positive square root divided by a negative square root is going to be one big negative square root, and the x squared gets distributed on the inside. 16x squared divided by the x squared makes the 16, plus 5 times 5 divided by the x squared makes it just plus 5 over x squared. Now when you take your limit as x approaches negative infinity, again a number divided by either plus or minus infinity, these terms go to 0. That leaves you with 5 divided by negative the square root of 16. And just clean it up. What's the square root of 16? 4. Negative that makes it negative 4. The answer is negative 5/4. This required a little extra thinking of the problem. Now, and here's the rule. When I take the limit as x approaches negative infinity and I have a square root of an x squared, I want to rewrite that as 1 over negative the square root of x squared. Okay? That 1 over x is negative 1 over negative square root of x squared. If I was going towards positive infinity, the limit as x approaches positive infinity, then I would have taken the 1 over x and turned it into 1 over the positive square root of x squared. The sign on the infinity is going to be the sign in front of your radical when it's a square root or even root, that is. Does that make sense? That'll lose you guys anyway. Well, one more problem and then we'll go on into section 2.1. Here was another kind of a problem that bothered students that had asked me a bunch of questions about. And so Here we go. Take the limit as x approaches infinity of the square root of x squared plus 8x plus 10 minus x. So officially, you plug in infinity. Infinity squared is infinity. 8 times infinity is infinity. Infinity plus infinity is even a bigger infinity. Plus 10 is even bigger. Square root of infinity is infinity. Minus x is going to infinity. It's the famous infinity minus infinity indeterminate form. As mentioned before, infinity minus infinity, well, sometimes it's infinity, sometimes it's negative infinity, sometimes they cancel and get 0 like you expect, and sometimes the answer is 45. It's indeterminate. You can't tell what's going on here. Okay? But in the problem that I did just before this, to do the limit as x approaches plus or minus infinity, you want a fraction. You know, polynomial over hopefully a polynomial, but sometimes they'll throw some kind of rational, radical something or other at you or whatever. But you got to have a fraction to do this 1 over x bit to it. So I got to make this thing a fraction. That's got to be the trick to it. Well, not a problem. Making him a fraction is real simple in this world. I can put a big old divide sign and stick him over 1. Now he's a fraction. Problem is I need polynomial or something or other. Function divided by function is really what I need. So I need to get rid of the square root of x squared plus 8x plus 10 minus x in the numerator. This is where we're going to use that conjugate trick again. So I'm going to multiply by the conjugate to get rid of this guy. The square root of x squared plus 8x plus 10. What's the conjugate of square root of x squared plus 8x plus 10 minus x? Square root of 8x, square root of x squared plus 8x plus 10 plus x. And what I do to the numerator, I do to the denominator. Now, I'm going kind of fast on this stuff, but I did make an awesome video for you guys to study while it was snowing and stuff, so you shouldn't be surprised by this. All right, now, what am I going to do? When you multiply by conjugates, you always FOIL out conjugate pairs. You leave non-conjugate pair stuff in factored form because hopefully the goal is to have something cancel here. So this ends up becoming the limit as x approaches infinity of, and I'm going to FOIL this out. The square root of x squared plus 8x plus 10 times square root of x squared plus 8x plus 10 is x squared plus 8x plus 10. Square and the square root cancels. The outer becomes plus x times the square root of x squared plus 8x plus 10. The inner becomes minus x times the square root of x squared plus 8x plus 10. And then last, minus x times a positive x is a minus x squared. Divided by non-conjugate pair, just leave a factor, 1 times the square root of x squared plus 8x plus 10 plus x. Now, you didn't have to write all this stuff out because you should know when you FOIL out conjugate pairs, the outer inner part will always cancel. But this one has some extra stuff canceling. What else cancels? X squareds cancel. So this leaves me with the limit as x approaches infinity of 8x plus 10 divided by 1 times anybody's square root of x squared plus 8x plus 10 plus x. And what this problem has just turned into is a problem just like the last one we just did. I'm taking limit as x approaches infinity, and I've got to figure out the degree of the top over the degree of the bottom stuff here. Look at and first off, I got to figure out what is the degree of the denominator. Well, I got a square root of an x squared. That really makes him a what? X to the first power, plus, and this is x to the first power, so the largest exponent is x to the first power. Remember, square root x squared, they cancel each other out. That's just x to the first power. So I'm going to multiply both the numerator and the denominator by 1 over x. Now, I'll go ahead and clean this up and distribute the numerator here. The limit as x approaches infinity of 8x times 1 over x is just 8, plus 10 times 1 over x is 10 over x. Now in your denominator, pay attention, you got 2 terms. And so I'm going to distribute over those 2 terms. One does not have a radical, so the 1 over x will do fine. The other one has a radical, and I need to rewrite 1 over x with the radical. Well, 1 over x is the same thing as what with the square root? It is 1 over the square root of x squared. But my question is plus or minus, and why? it's going to be the plus the square root. Why? Because this is the positive infinity that we're taking a limit on. Does that make sense? And so when I distribute this, combining a radical, square root divided by square root is one big square root. But the x squared divides throughout the inside. X squared divided by x squared is 1, plus 8x divided by x squared is 8 over x. 10 divided by x squared is 10 over x squared. Plus, and you got to do this guy, don't forget him. He's not inside the radical, so he gets the special, just multiply by 1 over x. And x times 1 over x is 1. Now take your limit as x approaches infinity, showing your work. All these terms with x in the denominator will always go to 0, and you're left with 8 divided by the square root of 1 plus 1, and square root of 1 is 1 plus 1 is 2. You get 8 halves, also known as 4. That's just 4. Again, I just wanted to take a few minutes here and just re-highlight all the stuff you're supposed to watch on the video, because you didn't have the option of being with me as I walked through it. You had to watch the interesting video on the virtual classroom day there. Moving on, section 2.1. All right, section 2.1 is going to be focusing on the concept of derivatives and rates of change. First things first, recall that the slope, fancy symbol for that is the famous M, is equal to the rise over run, which is equal to y2 minus y1 over x2 minus x1. But some of you also may know the slope formula as delta y over delta x. And what does delta stand for in mathematics? Change. So it's the change in y over the change in x. That's where you get your y2 minus y1 divided by x2 minus x1. Your classic slope formula. Now, what we're going to be focusing on in the beginning here is something called the slope of a secant line. Now, in layman's terms, a slope of a secant line to a function is this. You happen to have some kind of arbitrary function, and you're going to pick out 2 points on this thing. Now, here's x1 right here, and of course this would be f of x1 when you plot it. And over here I'm going to plot x2, there it is, and the y coordinate would have been f of x2. And with these 2 points that are actually connected on the function here, we're going to find the slope of the line that would connect these 2 dots. This is what they call the slope of a secant line, connecting these 2 points, x1 and x2. But it's a slope. And the formula for slope is change in y over the change in x. So this is where we get the y2 minus y1 divided by x2 minus x1, or better yet, f of x2 minus f of x1 divided by x2 minus x1. It's your slope formula. The only difference is these points are connected by some interesting function, but they would have given you x1 and x2. And hopefully you'll watch the awesome pre-section video some professor did for you guys. And so I did these guys on the video, so let's pick it up with number 2. Number 2, part A, states this. Find the slope of the secant line to the function f of x equals the square root of x between the points x equals 1 and x equals 9. Well, see, here's my problem here. X equals 1 and x equals 9 is not a point. It's a half a point. To have a point, you've got to have a y coordinate. So the first thing I'm going to do is get my y coordinate. So your y coordinate would be f of your x coordinate, that would be f of 1. The other y coordinate would be f of the other x coordinate, f of 9. Now remember, f of x is the square root of x, so f of 1 would be the square root of 1, so y equals 1, or you have the point 1, 1. Over here, we're plugging in x is 9, so y would be f of 9, which would be the square root of 9, and the square root of 9 is 3, so you get the point x was 9, y is 3. So to calculate the slope of the secant line, you can use the y2 minus y1 over x2 minus x1 standard form we memorized from junior high school, and plug in your coordinates. This is my first point, this is my second point. Change in y, it'll be 3 minus 1 divided by a change in x, 9 minus 1. 3 minus 1 is 2. 9 minus 1 is 8. Reducing my fraction, the slope of the secant line is 1/4. But, of course, where are we going with this? Well, take a look at part B. Find the equation to the secant line to the function f of x equals square root of x between x equals 1 and x equals 9. Anytime you hear these magic words, find the equation of the line, whether it be secant line or any other line for that matter, we don't care. Anytime you hear the magic words, find the equation of a line, you got to use the most famous equation of a line that nobody ever remembers. Give me an equation of a line. Y equals mx plus b. That's what everybody remembers. And that's an important one called the slope-intercept form. But it's not the most important one. It was the one that your teacher in junior high school drummed into your head. I'll give you that one. You know it to this day. Y equals mx plus b. And that line, slope-intercept form, is good. It's got two purposes in life. The two purposes are, it is used for graphing, calculator stuff, and it also is used for reading off data. Y equals 3x plus 2. The slope is 3, the y-intercept is 2. You can read off data. But the most important equation of a line is called the point slope. It is not pretty, but the point slope equation has one purpose in life. Find the equation of the line. That's what the point slope does. The point slope formula is y minus y1 equals m times parentheses x minus x1. You've got to have two things to use the point slope formula. We're math people, so don't think too deep in this. What two things do we have to have? A point and a slope. Well, we got 2 points up here. We got the point 1, 1 and 9, 3, 2 points, and we got the slope of the secant line being 1/4. So I got more than enough information. So pick a point. Doesn't matter which one you use. I have a brain though. I'll use this one I'm going to definitely use. Which one am I going to use? 1, 1. Smaller numbers, less chance to screw this up. Okay? Bigger the numbers, more chance you guys will screw it up. So use the small numbers here. Now use a point and a slope and plug it in. You plug in for the subscripts, you plug in for the m. The x and y without the subscripts, those are your variables. You get y minus the y coordinate, which was 1, equals the slope of the secant line, which is 1/4, times x minus the x coordinate, which is 1. Now, I'll be the first to admit to you that the point slope formula is the most important equation of a line, but it is not the prettiest. Well, the prettiest one is traditionally the slope-intercept form, the old y equals mx plus b thing. So let's convert this into that slope-intercept form. I'm going to distribute 1/4. I get y minus 1 equals 1/4 x minus 1/4. I'm going to add 1 to both sides. And this gives me y is equal to 1/4 x minus 1/4 plus 1 is what? Plus 3/4. And there is my equation of the line. The secant line that connects the points 1 and 9 on this graph. Does that make sense? Questions? Where are we going to do? Where is this going with? Take a look at the next problem. It says this. We are after this concept right here. The secant line's interesting, but what we're really after is something called the equation and therefore the slope of the tangent line. This is what we're drumming home with you guys. Estimate the slope of the tangent line to the function y equals x squared at the point 1, 1 by calculating the slope of the secant line between 1 and 1.1, 1 and 1.01, and 1 and 1.001. All right. So we're going to pretty much do the same thing here. We're going to estimate the slope. All we're interested in is the slope. So the first point we're going to go is between the point, remember, y is equal to x squared, new point. We got 1 point. When x is 1, 1 squared is 1. But the other point we want is 1.1. So to get the y coordinate, I want to take 1.1 and square it. That should be 1.21. There you go. 1.21. So this is my point, this is the fixed point, and this is the 1.1 point. So this is between x is 1 and x is 1.1. Okay? So now let's find that slope. I guess I could write it over here. The slope of the secant line here would be change in y with the change in x. And I'll do this, delta y over delta x, which would be equal to 1.21 minus 1 over 1.1 minus 1. Change in y over change in x. Now let's do some math without hurting ourselves. What is 1.21 minus 1? 0.21. Divided by what is 1.1 minus 1? 0.1. Now I do not need a calculator for this, and neither do you. What is 0.21 divided by 0.1? When you divide by 0.1, it's 1/10. It moves the decimal place one place to the right. And what do you get? 2.1. You didn't need a calculator for that. Does that make sense? All right, so between 1 and 1.1, we got the slope of the tangent line, the slope of the secant line being 2.1. Now we got to find the slope of the secant line between x is 1 and x is 1.01. Well, when x is 1, remember your y equals x squared. 1 squared is 1, so that's my fixed point there. The other point is 1.01. So to get that, I'm using my handy dandy calculator here, I'm going to take 1.01 and square him. And that gives me 1.0201. So calculating that slope of that secant line that we're talking about here, the slope of the secant line would be equal to, again, that change in y over the change in x, which will be 1.0201 minus 1, change in y, over the change in x, 1.01 minus 1. Again, you don't need a calculator for this. 1.0201 minus 1 makes it 0.0201 divided by 1.01 minus 1 is 0.01. And when I divide by 0.01, what overall effect does it have? It moves that numerator decimal place 2 places to the right, and I get 2.01. Does that make sense? So the slope of the secant line between 1 and 1.1 is 2.1. Between the 1 and 1.01 is 2.01. And they wanted me to do it one more time. We get x is 1 and x is 1.001. So again, your function is still y equals x squared. So between 1 squared is 1, so your fixed point is still there, 1, 1, 1. Your other point, your x coordinate is 1.001. You've got to figure out the y coordinate of it, so we're going to take 1.001 and square it, and we end up getting 1.00201. And now calculating that slope of the secant line between these two guys, which officially is your change in y over the change in x, will be 1.00201 divided by, minus 1, divided by 1.001 minus 1, change in y over the change in x. That gives you 0.002001 divided by 0.001. And when you divide by 0.001, it moves the decimal place 3 places to the right, and I end up getting the slope of a secant line is 2.001. But if you go back and look at what we've done here, is we found the slope of a secant line on this particular function right here. Here's my point, 1, 1. We went from 1 to 1.1. Then we went from 1 to 1.01. Then we went from 1 to 1.01. We are actually doing the limit. The limit as the distance between these 2 points is getting smaller, going towards 0. And therefore, when you do that, you get something called the slope of a tangent line. A tangent line is a line that just comes in and just touches that graph at that particular one spot and then just moves off in a straight line. And it's going in the same flow as the actual function. So based upon the information here, can you tell me what is the slope of the tangent line connecting these 2 points? Well, actually at the point 1, 1 of the function y equals x squared. Well, it's 2.1, then we got closer, 2.01, 2.001. What number do we seem to be approaching here? The answer is 2. Does that make sense? Questions? I got a question for you guys. Right. Before we move on to our next problem here. Well, first off, we'll talk about this, and then I'll have my question here. All right. So, a generalization of the previous example gives us a definition. The slope, or the slope of the tangent line, if you will, is equal to the limit as x approaches a of f of x minus f of a over x minus a. Excuse me. The slope of the tangent line can alternatively be calculated by the following way. So we're going to use x as arbitrary here. We have a point x. And h is a distance to another point, x plus h. And here's a point, here's x, and we plot him, here's f of x. Here's another point, x plus h. So the distance between these 2 points is h. H is the distance. You plot him up here, and the y-coordinate is going to be f of x plus h. Now, to actually get the slope of the tangent line at this particular point, it's a slope, so I'm going to find the slope between these 2 points. So your slope is change in y with a change in x, or change in y, f of x plus h minus f of x divided by x plus h minus x. Well, when you clean this up, clearly the x is canceled here, and you get divided by h. And you get a formula that I know you guys that took high school math 3 or whatever it happens to be called these days, that we call it basically pre-calculus, that you no doubt have seen before. It's called the famous difference quotient. F of x plus h minus f of x all over h. They drum that in any kind of pre-calculus class. They drum that formula into your head all over the place, but they never tell you why. The reason why is because it's actually the definition of the basically the slope of the tangent line, and it's something we're going to be using in calculus here. Now, to figure out the actual slope of the tangent line, and let's put subscript tan over here, the slope of the tangent line, what you want to do is you want to make this distance 0. You want to get it closer and closer and closer. So that the points being here, bring the point closer and closer and closer and closer, and all of a sudden you got the 2 points on top of themselves. Basically, you're taking the limit as the distance h goes to 0 of this f of x plus h minus f of x all over h. This is a very important formula called the slope of the tangent line definition. Okay? So, introducing notation to you guys and definition. The definition of derivative is this. To be the derivative, it's f with a little prime on it. Okay? F prime. This is basically from the Newtonian notation. You can blame Sir Isaac Newton for this one. He's the one that developed calculus for us. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. It is your slope of your tangent formula, but when you have arbitrary x's in this thing, you're going to get a derivative function that will be based upon x. However, that also means this. If I want a particular slope of the tangent line, this is important, so make sure you get this in your notes. The slope of the tangent line at x equals a is known as f prime evaluated at a, which would be equal to the limit as h approaches 0, but instead of arbitrary x, we're going to use a That'll be f of a plus h minus f of a all over h. So this f prime of a is also known as the slope of the tangent line at a. And we have two formulas for the slope of a tangent line at a particular point. You have this formula here, which is your limit as h approaches 0 of f of a plus h minus f of a all over h. That's f prime of a. And that other formula we just discussed, which is f prime of a is equal to the limit as x approaches a different kind of limit, of f of x minus f of a over x minus a. Okay? Now, before I move on and get into the great lecture on this stuff, I got a question for you guys. Who cares? Why do we need to know this stuff? Slope of a tangent line. Who cares about tangent lines? Well, I got a question for you. History question. See if you guys know any history. What happened in Earth history in 1969? You guys have any idea? 1969. I know it's before you guys, most of you guys were born anyway. 1969. What happened? What? Moon landing. What was the name of the mission that got to the moon? Apollo 11. Good. Be amazed how many people tell me Apollo 13. No, that's that crappy movie with Tom Hanks. Apollo 11 actually is the one that actually made it to the moon the first time. Apollo 13 actually didn't make it to the moon. You should watch the movie. But my question to you is this. How did we get there? How did we get to the moon? All right. Okay, this is supposed to be Florida. Okay. Okay, South America down there. All right, I don't know. The North Koreans attacked or something. I don't know. It is. All right. There is Florida right there. All right. There we go. And there's Asia, and there's Europe. Okay, so there it is. Earth. Okay, in case you didn't know. Earth. There. So it's even better. All right. Moon. Here, I'll put some more on there. Okay. In case you didn't know about that either. Moon. So, we had to, at Cape Canaveral, we had to launch what we call a Saturn V rocket, otherwise known as an intercontinental ballistic missile. Okay? Von Braun helped us discover this. Von Braun is a famous German rocketeer, if you will, rocket scientist from Nazi Germany. That's right. We even stole the guys from the Nazis. So he was very, very bright about these rockets and stuff. And with our help and a huge amount of money, we created a Saturn V rocket. The problem with the rocket is it takes almost all of its energy just to get outside the Earth's atmosphere, get out of gravitational pull. So you see the rocket had to actually be launched, and then you see these stages kind of break off once that particular section of rocket was used up. Well, it was dragging us down because of the weight, so it would be ejected, and then eventually the rocket launched, and it went up here, and we finally got to orbit. All that energy on that huge rocket just to get a capsule, which is about from here to about here to orbit. Okay? We did something called the slingshot effect. You know what the slingshot effect is? We used the Earth's gravitational pull. So we didn't actually go in a circular fashion. It was more of an elliptical fashion. So over here you slow down and then you kind of get a little bit close to Earth and you speed up thanks to gravity, and we kind of speed up here and then speed up and speed up and speed up and speed up. And remember, the moon is orbiting the Earth, so this is a beautiful mathematics here. So at the right time, when the moon is coming over here, we had to hit our little retro rockets, and boom, and we got away from the Earth's gravitational pull, and we kind of try to get ourselves sucked into the moon's gravitational pull. Okay? And then there was a little capsule called the moon lander on top of our rocket that we actually landed on the moon, and then we left a bunch of garbage behind and got the little top part of it, went right back up here and actually got back and got the men back onto the capsule, and then they did the slingshot effect here, and then they hit the retro rockets and just pushed themselves out of the moon's gravitational pull, and then actually went more like this way, and then we ended up landing ourselves into the Pacific Ocean down here. Okay, and we actually got back into Earth and actually got there. But do you know what this is right here? When we left that Earth's orbit here, and we took that hit those retro rockets, what this actual line is called before it actually was sucked into the moon's gravitational pull? That's right, beautiful calculus, tangent lines. And we use tangent lines here, we use tangent lines right here, and just to let you know, we actually got to the moon a lot faster than we got back from the moon, because remember, the moon's gravitational pull is 1/6 of that of Earth, so we could only speed up so much on this thing before we hit it back and stuff. So, I mean, it's beautiful mathematics and beautiful science on this stuff of how we got there. And timing is everything, because if we didn't hit the retro rockets in the right thing, if the moon was over here, we'd have kept on going. Mars or someplace before we would have stopped and stuff. So, very, very important science effect and stuff like that. So, I tell you these stories because I want you guys to get motivated of why it's important. Because you're going to use this stuff a lot in your science majors, STEM education, with engineering, math, obviously, science, physics, chemistry, biology, computer science. There's so many applications of the things that we do in this stuff. Okay, and this is just to give you a visual here. Now, hopefully you'll watch some awesome pre-section videos here, and no reason for me to go back over those things again. So let's pick it up with this guy right here. Question is this: find the equation of the tangent line to the function f of x equals x squared minus 3x plus 1, where x is equal to 5. Okay. All right. Now, I know what I'm about to show you guys is an easier method for this stuff. Don't care. We want to make you work the algebra. There's we're trying to reinforce your algebra skills, so I'm doing it a particular way, and we expect you to do it the exact same way. So, first thing if I want the equation of a tangent line, all right, this is right up. Find the equation of the tangent line. Anytime you hear the word find the equation of a line, what am I going to use? Point slope. The formula for point slope is y minus y1 equals m times x minus x1. But it's not just any slope, it's the slope of the tangent line, right? But to use a point slope, you've got to have two things. What are those two things? We're math people. Don't think too deep in this stuff. Point and a slope. Well, we're supposed to find this slope of the tangent line thing of this equation, f of x equals x squared minus 3x plus 1, where x equals 5. I mean, they can't even give me a point. What do they give me? A half a point. X is 5. How do I get the y coordinate? I plug it into the original equation, f of 5. This would be 5 squared minus 3 times 5 plus 1. 5 squared is 25 minus what? 15 plus 1. 25 minus 15 is like 10. Plus 1 is 11. Sorry, page there. Okay? Does that make sense? 11. So the point is 5, 11. I got my point. The other thing I need to have is a slope. The slope of the tangent line is also known as the derivative evaluated at the point. In our case, our point is 5. Okay? Getting used to the derivative notation here. Now, here we go. There are two formulas that I can use to get this thing. The two formulas are, and this is for your note-taking abilities here, f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. And the other f prime of a formula, I put the word or right there, is the limit as h approaches 0 of f of x minus f of a over x minus a. Oh, excuse me, this x approaches a there. Sorry. Limit as x approaches a of f of x minus f of a over x minus a. There are two formulas you can use to get this thing. And it honestly, unless we tell you, it doesn't matter which one you guys use. I can use the limit as h approaches 0, the one we focused on a few minutes ago, f of h, a plus h minus f of a all over h, or I can focus on this one, the limit as x approaches a of f of x minus f of a over x minus a. Which one would you guys prefer using? Bottom one or top one? I hear people going either ways. Do you know which one's easier? It's always the one I like to go with. You know what's the easiest one? Bottom one. Bottom one's easier. The top one has more algebra to do. All right? And I'll prove it to you in just a second here. I'll prove it to you. But I'm going to go for this one quick. So if I'm going to sit there and find the derivative at a particular point, I'm going to try this guy here. My choice. I'm the professor. I'm going to use the bottom one. Why? Because it's going to be the fastest one. Here, a is equal to 5. So this slope of the tangent line, which will be f prime of 5, would be the limit as x approaches a, but a is 5, of f of x minus f of a, which is 5, over x minus 5. So my derivative at 5 is the limit as x approaches 5 of f of x. Well, they gave me f of x. That was x squared minus 3x plus 1 minus f of 5. I just calculated f of 5 a few minutes ago. What was that? 11 all over x minus 5. So let's clean this up. Slide this up a little bit. You guys can see this. So let's clean this up. So f prime of 5 would be equal to the limit as x approaches 5 of x squared minus 3x plus 1 minus 11. You can drop the parentheses here. All over x minus 5, which is the limit as x approaches 5 of x squared minus 3x. Let's see, plus 1 minus 11 is what? Minus 10 over x minus 5. It turned into one of them chapter 1 kind of questions here. What's the first rule of limits? Plug it in. And when you plug it in, this will happen to you every time. 5 squared, 3 times 5, 25 minus 15, minus 10, yep, 0. And 5 minus 5, 0. What a surprise. That's why we beat this stuff to death. 0 divided by 0. And what does 0 divided by 0 mean? Do algebra. Okay? So this f prime of 5 would be equal to the limit as x approaches 5 of, now that x squared minus 3x minus 10 factors, the denominator is pretty much set. It's x minus 5 here. But how does x squared minus 3x minus 10 factor? It factors x. What times what is 10 that differs by 3? It's got to be what? 2 and 5. And it'll be middle terms minus, opposite signs because the minus here will be minus on the 5 plus on the 2. What a surprise. And guess what? With the 0 divided by 0, somebody's going to cancel. What cancels here? X minus 5's cancel. So this is equal to the limit as x approaches 5 of x plus 2. And when I plug it in, I get 5 plus 2, which is 7. Does that make sense? Now, I went out of my way not to skip any steps with you guys on this stuff. But at the end of the day, the slope of the tangent line, or f prime of 5, is equal to 7. Oh yeah, what was the question here? You were supposed to find the equation of the tangent line. Here is my point, here is my slope, and here is my formula, the point-slope formula. So y minus y1 equals m times x minus x1. Y minus my y coordinate, which was up here 11, equals the slope, which was 7, times x minus the x coordinate, which was 5. And there is the equation of the tangent line. Not pretty. It's the point-slope formula. So I'm going to distribute this guy out and put it in slope-intercept form, the old y equals mx plus b. This will give me y minus 11 equals 7x minus 7 times 5, 35. I'm going to add 11 to both sides. And I get y equals 7x minus, minus 35 plus 11. What was that, 24? Y equals 7x minus 24. There is the equation of the tangent line. Do I lose you guys anywhere? Now, and I know you're looking at this going, this was the easier method? Yeah. The reason why is because when you use this method, this little formula for the derivative, it's going to turn into a classic polynomial over some linear factor, and the polynomial on top will factor and basically do the stuff that we did before. Now, try this one. A person standing on top of a 200-foot building throws a ball into the air with a velocity of 96 feet per second. The function s of t is equal to negative 16t squared plus 96t plus 200 gives the ball height above the ground t seconds after it was thrown. Find, fancy words here, underline them because I'm trying to work problems, get you guys to understand what you're supposed to do. Find the instantaneous velocity of the ball at 2 seconds. Okay? Now, velocity, by definition, is change in distance over change in time. To do the instantaneous velocity, let you guys know, instantaneous velocity at, what was our time saying here? At time equals 2 is the same as s prime of 2. The derivative is the instantaneous velocity. When you take the derivative of distance, you get velocity. When you take derivative of velocity, you'll get acceleration. We'll go into the physics a lot later. But so instantaneous velocity, because it's change in distance over change in time, you're basically looking for your derivative here. But I want to show you this problem doing this one. So this one's going to be s prime of a. I'm going to use this formula. The limit as h approaches 0 of s of a plus h minus s of a all over h. You replacing f with s because that's the function they gave me. Does that make sense? Here, a is equal to 2. So this would be the limit as h approaches 0 of s of 2 plus h minus s of 2 all over h. This would be equal to the limit as h approaches 0 of, here we go. What is s of 2? Remind you, s of t is equal to negative 16t squared plus 96t plus 200. Right? Just recopying my formula now. And I don't care what's inside the parentheses. This is college algebra. Whatever's inside the parentheses is what I stick in for the t in this example in the s of t formula. So this would be negative 16, and we're doing s of a plus, s of 2 plus h here. So that'll be 2 plus h squared plus 96 times 2 plus h plus 200. That right there is s of 2 plus h minus s of 2. Well, I'll use the calculator for that. S of 2, just to let you guys know, s of 2 is going to be negative 16 times 2 squared plus 96 times 2 plus 200. Negative 16 times 2 squared plus 96 times 2 plus 200, 328. All over h. Now, let's do the limit. First thing I'm going to do is I got to clean this mess up. This is the limit as h approaches 0 of negative 16 times 2 plus h squared. I got to full it out. That'll be 4 plus 4h plus h squared. Plus here I'm going to distribute 96 times 2 is what? 192. 192 plus 96h plus 200 minus 328 all over h. This will be equal to the limit as h approaches 0 of, I'm going to distribute the negative 16 here. Negative 16 times 4 is negative 64. Negative 16 times 4h is negative 64h minus 16h squared plus 192 plus 96h plus 200 minus 328 all over h. This is equal to the limit as h approaches 0 of combine like terms. Watch this. What is negative 64 plus 192 plus 200 minus 328? I'll do it on the calculator to show you. Negative 64 plus 192 plus 200 minus 328. What you get? 0. It all cancels. All the constants. That's a check, by the way. It'll always happen like that. Can cancel. You're left with, combining like terms, negative 16h squared, and you got a minus 64h plus 96h. That's it. That gives me with a plus 32h. That's 32h all over h. Well, right now, you know if I plug in 0, what am I going to get? 0 over 0. So I'm going to now, after cleaning it up, I'm going to do more algebra on this thing, but I can factor out an h. This is the limit as h approaches 0 of, factoring out the h, I'm left with negative 16h plus 32 divided by h. The h is canceled, so this is equal to the limit as h approaches 0 of negative 16h plus 32. And when you plug in h is 0, negative 16 times 0 plus 32. Notice I don't write limit anymore. That goes away, and I get 32. So, in other words, s prime of 2 is equal to the velocity, and that would be the instantaneous velocity at x equals 2, which is 32. And because it's a physics problem, how would you rank the units on a problem as this for the velocity? Well, the distance is measured in feet, the time is measured in seconds, so that would be what? Feet per second. There is my instantaneous velocity. But my point to this was, well, which formula was better? Well, you got to learn how to use both of them, but you'll see that other formula, if you need a slope of a tangent line at a particular point, the little f prime of a equals f of x, limit as h of x approaches a, of f of x minus f of a over x minus a, is a little faster in terms of the algebra, but you're going to have to do both. Okay? So, web work problems. The position of a particle is given by this chart table there. You got seconds, 0, 1, 2, 3, 4, 5, and you got feet, 0, 14 feet, 47 feet, 51 feet, 86 feet, 103 feet. Find the average velocity for the time period beginning at 2 seconds and lasting 3 seconds. So if you start at 2 seconds and you last 3 seconds, you end at 5 seconds. So the formula for average velocity, that's different from instantaneous velocity. That'll be basically the distance at time 2 minus the distance at time 1 over time 2 minus time 1. Change in distance, s represents distance by the way, over change in time. So these are your times, 2 seconds to 5 seconds. So it'll be s of 5 minus s of 2 over 5 minus 2. S of 5 is 103 minus S of 2 is 47 divided by 5 minus 3. Screwed that up. 5 minus 2. Well, 103 minus 47 is 56. And 5 minus 2 is 3. And 56 divided by 3 is, just for you guys that want to know, 18.66667. And this is in feet, this is in seconds, so this will be feet per second. On web work, don't type in the units, okay? But you need to know units for my kind of test and stuff. Does that make sense? Look at the second one. What is the average velocity? Again, starting at 2 seconds and lasting 2 seconds. So if you start at 2 seconds, where is your end time going to be? 4 seconds. So your average velocity would be equal to S of 4 minus S of 2 over 4 minus 2. Okay? S of 4 is going to be 86. This is where I used the chart. Minus S of 2, still 47, over 4 minus 2. 86 minus 47 is 39. 4 minus 2 is 2, and 39 divided by 2 is 19.5 feet per second. So the average velocity between 2 and 5 seconds was 18 and 2/3 feet per second. Their average velocity between 2 and 4 seconds was 19.5 feet per second. What about starting at 2 seconds and lasting 1 second? So that means I'm going to start at 2 seconds, but I'm going to end time is at 3 seconds. Okay? So this average velocity would be equal to S of 3 minus S of 2 divided by 3 minus 2. S of 3 is 51 minus S of 2 is 47 over 3 minus 2. 51 minus 47 is a whopping 4. Divided by 3 minus 2 is 1. That gives me 4 feet per second. So if I go back and look at it from a physics perspective, the average velocity between 2 and 3 seconds was 4 feet per second. It was going slow. But then the average velocity between 2 and 4 seconds zoomed up to 19.5 feet per second. So what must have happened between that 3 and 4 seconds to get my numbers the way they did? It must have accelerated rather quickly. And then I'm now at 19.5, but then to go from 2 to 5 seconds, I'm at 18.67. It must have slowed down slightly to drop down my numbers to 18 and 2/3. So again, analyzing the physics. Take a look at number 19. Some of these questions are pretty lame, but it's the wording more than the question that throws people off here. The equation of the tangent line to the graph of y equals g of x at x equals 3, if g of 3 equals negative 3 and g prime of 3 is equal to 7, is y equals what? They want you to find the equation of the tangent line. So what am I going to use? Point slope. Y minus y1 equals m times x minus x1. You need to find the equation of the tangent line, but you got to be able to read the information here. G of 3 equals negative 3. G of 3 equals negative 3 means you actually have a point. What was the x coordinate? 3. What's the y coordinate? Negative 3. And that g prime of 3 is equal to 7. This is that new notation. This g prime is the derivative. Evaluated at 3 is 7, so your slope of your tangent line, which is your derivative, is 7. There's my point. There's my slope. You had to read it off from the notation. Does that make sense? Does that make sense? So, plug it in. Y minus the y coordinate, negative 3, equals my slope, which is 7, times x minus the x coordinate, which is 3. So y plus 3 equals 7x minus 21. Subtract 3 from both sides. I get y equals 7x minus 24. Last one for the day. Part B. If the tangent line to f of x at 210 passes through the point 0,4, then what is f of 2? And what is f prime of 2? This is how they're going to drum this notation into your head. F of 2, that's the y coordinate at 2. What's the y coordinate at 2? 2, 10, it's got to be 10. Does that make sense? The point 2, 10 this means this is f of 2. It's the point. But f prime of 2 is that slope of the tangent line, right? So the slope of the tangent line, slope of tangent line, would be y2 minus y1 over x2 minus x1. I'm going to use my 2 points. Change in y, 4 minus 10 divided by change in x, 0 minus 2. 4 minus 10 is what? Negative 6. 0 minus 2 is negative 2. Negative 6 divided by negative 2 is 3. So f prime of 2 has got to be that slope 3. Does that make sense? Questions? I will finish up. There's 2 more problems for this about using the web work. And it's a great place for me to start next time as I'm going to jump deep into section 2.2. See you guys then.
Hey, can you pull that word back up so I can finish writing with it?
Which one? This one right here? Sure.
Yes.